Hello, class. Today we're going to be continuing on with conditional statements, but we're going to be focusing more on the aspect of negation. Negation is basically, giving you a little preview rundown, is when you look at a statement, you say, well, this is not the case. For instance, you see this how I have a red laser pointer going around in circles right now. A negation of that would be hey, that laser pointer is not green, which is a true statement since there are green laser pointers out there. Let's just give you a little bit of a preview. Anyways, so we're going to go ahead and have a little warm up. And what we're going to do with the warm up is we're going to say what is the hypothesis and what is the conclusion of this following statement. The statement we're looking at is if you truly want to change your life, then you must be willing to change your outlook on life. So we might be getting a little bit more into the psychological aspects of today about how this obscure area of mathematics can be more on the psychological aspect of things or philosophy and things like that. But it's just a weird spot in mathematics, but it is part of mathematics. Anyways, give it a pause, give it a go. When you feel ready, go ahead and resume. Okay, welcome back. So if we're looking at the hypothesis, remember we're looking for the word if. So in this case, if we're looking at the word if, we see that we have an if right here. All right. And we're looking for the word then as a flag word for the next part. So let's go ahead and have a look there, and then I'm going to switch back to the laser pointer, and we're going to go. So the hypothesis is if you truly want to change your life, then you must be willing to change your outlook on life, is the conclusion. And overall, this is a true statement. You can either always say everything's wrong with my world, everything's wrong, everything's wrong, everything's wrong. The whole lead a horse to water and they can never force it to drink kind of thing plays here too. So there's plenty of things that you can actually apply this to. Some people say, well, they're bad at math, they're bad at math, they're bad at math, or they're bad at this subject or that subject. And it's because you keep saying that you eventually believe that. So if you want to be decent at a different skill, you must be willing to change your outlook on how you look at that skill. All right. So this is day 2 of the conditional statements, wordplay, but with mathematics. And as already stated, it might get a little deep today. Let's keep on going on our journey. So remember, we did cover the converse today. So we're going to be looking at the negation. Well, in the book it says not P, but it's not just limited to P. We can look at other things, and we'll see how that works here in a little bit. The inverse is not P. If not P, then not Q. We'll see how that works a little bit as well. And then the contrapositive is basically the inverse of the converse. As you see, we switch the if Q and P, we switch the Q and P around. But this time we're going to switch them and take the negation version of it. In other words, we're going to take the opposite of it. Say not this. If our hypothesis is wrong, then if our conclusion is wrong, then our hypothesis is wrong. Swap them, basically. So let's go ahead and get into it. As you see, those are the 3 we're covering. And here we go. So negation of a statement has the opposite meaning of the original statement. So the statement was taken from the book, so this is something to be aware of. Negation doesn't just affect our hypothesis. All right. If you look at this image, we first want to notice what kind of animals are here. You might have one of your own, and some of them might be more aggressive. I've always been bitten by hamsters, for example, so I'm not a big fan of hamsters. And I always considered the Chihuahua. This is a part of it. Looks to be a type of Chihuahua. Kind of has that face. To always be a little dog trying to think it's a big dog, and you just look at it and it'll start cowering and shaking. Anyways, I digress. Let's go ahead and have a look here. The statement I'm making, I'm going to grab this and move this down, is if I'm in this photo, then I am the dog. So if we're going to be talking about negation, let's start with that. Do you always have to be the dog in order to be in this photo? So the hypothesis is if I'm in this photo, then I am the dog. Assuming that these animals could talk, can only the dogs talk? We're not all Scooby-Doo. So we can assume that other animals can talk. After all, there were other cartoon shows that had talking animals. I'm pretty sure you can think of one where there's been talking birds, like Rio, and there's also talking rabbits and stuff like that in Zootopia. And cats, I think we're also in Zootopia, but there's also the cat and cat dog. So there's plenty of other animals. There's Courage the Cowardly Dog and talking snakes and various other Disney movies like Jungle Book. Just thinking about Disney movies. And of course, there's Finding Nemo right here. So that doesn't necessarily mean if you're in the photo that you have to be the dog. So let's switch that. So if I'm in the photo, then I am not the dog. So that just eliminates this dog and this dog. That means all those other critters could be the one in the photo, and that changes a part of it. So we're kind of having an opposite meaning. We're either the dog or we're not the dog. So it's just working with that. All right. Let's look at this and negate different parts of it. Most people think they want to be rich, but is that an actual reality? Yes. Being rich, I had an aunt that once told me, being rich makes it so you can have certain nice things. For instance, she lived in a nice part of San Francisco, not San Francisco, but Santa Rosa. She lived in the ritzy part of Santa Rosa and took multiple cruises every year because she was quite wealthy. But a lot of people think if they are rich, then they are happy. Okay, so let's just bring this down a little bit first. If I am rich, that is the hypothesis. Then, only after that, I am happy. Okay, so if we're looking at negating the P, if I am not rich, then I am happy. Is this possibly true? For some, yes, and for some, no. It just depends on who you are. Some people are so obsessed with trying to get more money that they lose sight on what they have. And we'll go into more detail about that in a moment. But just know that you could not be rich, but you're still happy. Well, rich meaning in financial rich, because you can be rich in other things. Things that the people who are actually financially rich don't have. All right. Not Q is looking back at this statement and saying, negating just the Q. If I am rich, then I am not happy. So if we're talking about financial wealth, if I am rich, then I am not happy. This would actually describe my aunt. Yes, she was rich, but one thing she always said is this: being rich, you do not know who your friends are. And it's quite lonely. Yes, you might have a lot of people that say they like you, but you can never be sure that they like you for you or they like you for your money. And they only want your money out of you. It's very hard to tell. And some people only like you because you're rich. They're not interested in your money, but they only like you because they are rich and you're rich. And they tend to be quite snobbish. So she said, like, yes, I can take these cruises. Yes, I can live the life of luxury as many people want. But the life of luxury is actually quite lonely. I know that that most of my family still loves me, but there are some family members who only want me for my money. So yes, having a lot of wealth can make life easier. So you can buy anything you want, mostly anything you want. You can buy houses, you can buy clothes, you can buy toys like cars and things like that. And in many ways, you buy friends. Friends come out of the woodwork just to be with you because you're rich. But if all that goes away, you'll be left with you'll be able to see who your true friends are. And they might not be the people you think they are. So that's why this is kind of like a loaded question, because you could not be rich financially, but you could be happy looking back at this one. You could not be rich financially, but you could be happy because you're rich in life. You know what you have. You know who you're friends with are with, you know your family, you know people who like you for you. And you could be rich in other aspects, not just financially. You could be a great person. So it's just something to think about. As I said, it's probably going to get a little deep today. So when we look at not P implies not Q, we're actually looking at the inverse. That's why it switched up here. So it's obtained by negating both the hypothesis and the conclusions of the conditional. So negating both, you try to make it make sense. So you say, if I am not rich, then I am not happy. This statement could easily apply to anyone who thinks being rich will make them happy. That they are not happy as long as they are not rich. But the question is this: will they ever be happy? Because sure, you say, well, if you're one of those people and say, sure, I'll be happy as soon as I'm rich. But if you were able to get rich, there's always something else you don't have. And whatever that is, you will replace the rich with that. And you will not be that anymore. You want that. You want that. You'll always be wanting more if you fall into this trap of just because you're not rich, you're not happy. Of these statements, two that make sense is if you know who your friends are and you're rich, this might be, and you're happy with what you have. This one makes sense. And the other one that makes sense would be the second one, because the other two imply that you're not happy with your present conditions. So it's always to have the end result where you're actually happy, even if you are or are not rich. All right. So you see how we can just take the statements and play with them slightly and go from there. As you see, if you start down here and somehow gain wealth, you kind of loop back up to here. You'll be rich, but there's something else you don't have, and you wouldn't be happy at that point. So create and evaluate the inverse of the following statement. If a shape has three sides, then the shape is a triangle. So the inverse is we're saying not the first part, not the second part. So we want to try our best to create a sentence that makes sense. So we look at the fact that if a shape has three sides, that's the hypothesis, then the shape is a triangle is the conclusion. So if a shape does not have three sides, then the shape is a triangle, could be an inverse of it. But then we also have to get the other part. So we first start out getting the inverse of the first part, get the inverse of the second. The shape does not have three sides, and the shape is not a triangle. That makes sense, because only triangles have three sides. So logically, that makes sense. All right. We'll see multiple ways to work on this one. So we're going to create an if-then statement of the following, and then create the inverse and evaluate it. So two identical angles sum to 180 degrees. So we're going to try to create an if-then statement, and then create the inverse. So if we have two identical angles, this is one way we can look at it, then the angles sum to 180 degrees. That's not necessarily true. For the statement, it's what's asking for, but it's not necessarily true, because two identical angles does not mean that angles have to be 90 degrees. They can be 30, they can be 45, they can be anything that you can have two of. Heck, they can even be two angles of 1. 1 plus 1 is 2. 2 plus 2 is 4, etc., etc. You can do that all the way up to 90, so there's 90 different options. Technically, you can even have 0, but that's not mathematically sound, or makes a lot of sense mathematically to have an angle of 0 degrees. Anyways, I digress. The other way you can look at it is if you have two angles that sum to 180 degrees, then the angles are identical. Again, for the question, that's what it's asking for. But in regards to it making this being the only case, that's not true. Because we can have 120 plus 60 is 180. Think of all the different ways you can just add two numbers together to get to 180. But they're not all identical. Only one is of those. So one of 179 about, that's a pretty low chance of being this one case. And we'll talk more about probability later on. So, negating. If we do not have two identical angles, then the angles don't sum at 180 degrees. We have talked about this. We can't have 60 and 120 and have that sum at 180 degrees. So this is a false statement. 60, 120, 80 and 100. You can probably think of some more that are not 90 and 90. All right. So if two angles don't sum to 180 degrees, then the angles aren't identical. That too is false, as we already kind of talked about. 30 and 30, 20 and 20. 20 plus 20 is 40, and 40 is not 180 degrees, but they're identical angles. So we can have 40. We can have a 40-degree angle that's not summing up to 180 degrees, but they are identical, so that's a false statement as well. Pretty simple. All right, contrapositive. It's just kind of like what we were doing yesterday, taking the converse, flipping these two back and forth, and then negating them. So let's look at the statement. If it's raining, then a non-covered parking lot is wet. By now, the name of the game is pretty easy to identify the hypothesis and the conclusion because you look for the keywords if and then. If. That was supposed to be then, sorry. So this is actually supposed to be an N right here. So if it's raining, then the non-covered parking lot is wet. So we forgot a then right here. Sorry about that. So if the non-covered parking lot is dry, then it is not raining. Okay. So we took the negation of wet. Something that's wet, we want to make it so it's opposite. So it's not wet. So we think dry. And if it's raining, we want to make sure it's not raining. Okay. Well, if non-covering parking lot's dry, think of your average like Walmart parking lot, shop, or Safeway parking lot. Just a couple of chain stores to think about. Could it be dry when it's not raining? Or could it also be dry when it's raining? Well, it depends. Sure, it's not covered, but there could be dry spots like under a car. So even then, it can be a little bit yes or no. This one's a little bit vague because there can be certain very specific conditions to make a dry spot. But it's implying here that it's the entire parking lot, not just that spot. So you have to be kind of careful about that. All right, let's look at this one. If the number is even, then it's divisible by 2. Okay, so we're looking at if the number is even, then it's divisible by 2. Okay, switching around. If a number is not divisible by 2, let's take in this part, bring it over, and negating it. So if it's this one's saying divisible by 2, we want to say it's not divisible by 2. That's what it says over here. That means we want to bring this down and say the opposite of this after the then. Then it is not even. Then the number is not even. So we kind of want to be careful about how we do this. We want to make sure it still makes sense what you're talking about, because just think about it this way. If a number is not divisible by 2, then it's not even. Overall, it makes sense, but it makes a little bit more sense to say if a number is not divisible by 2, then the number is not even. That makes a tiny bit more sense, at least to me. But if the other way makes more sense to you, more power to you. All right. So, is this a true statement? Well, if it's not divisible by 2, then it's clearly an odd value because there's no even number besides 2, which 2 is divisible by 2. That's not divisible by 2. That's basically there's no even number that's not divisible by 2 is what I'm trying to say, because 2 is the only prime even number. Anything that's even is then divisible by 2. So that does make sense. And we can say, yeah, that's true. All right. So, if you have two numbers that are odd, their sum is even. You have to remember what the word sum means. So first focus on that. There we go. First focus on that. A little bit of a tongue tie right there. Sum is addition. So we're saying that if we have two numbers that are odd, when we add them together, we're going to get an even result. That's true. You can look at a little bit of number theory to prove this to be true, but think of any two odd numbers. For instance, 1 and 3. 1 plus 3 is 4. 4 is even. 3 and 5. 3 plus 5 is 8. 8 is even. 21 plus, 23. 3 plus 1 is 4. It will still be even. You can have 5,642,839 and have, 68,332,007. It's the last digit that matters. That digit in the ones. And you're always going to end up with a 1, in a sense, a 2n plus some sort of odd value plus another certain sort of odd value. It's going to cause that odd value to become even every single time. So the original statement is true, is what I'm trying to get at. So let's get back to it. What is our original hypothesis? We're looking for the word if and flagging what's behind it. What is our original conclusion? We look for the word then and tag what's after it. So if two numbers are odd, then their sum is even. So in order to take the contrapositive of this, we're going to switch them. We're going to take the sum is even and switch that first. So for right now, we're saying the sum is even. Negating that says the sum is now odd. If the sum is odd, if the two numbers sum is odd, this is where we have a couple different ways to look at this. Because we originally said that two numbers are odd, but we're nowhere dealing with two numbers. So we have, and both numbers are not odd, but there's different ways to look at this. That means both our numbers could be even, but that doesn't necessarily make sense. Because 2 plus 4 is 6, and 6 is not odd. Then we're looking at least one number is odd, or at least one number is even. So it's just different ways to look at it. But it's more likely one number is odd and one number is even is what we're really trying to get to in order to make the statement true. Because this one has too much vagueness to the point where if they're both even, it makes it false because you can't get an odd value by adding two even numbers. These two, at least one number is odd and at least one number is even, implies you have a 1-to-1. At least for this one. This one has a little bit of vagueness like this because at least one number is even. That means they both could be even. Going back into this problem up here. So probably the best way to go about is, since we started with two numbers being odd, saying at least one number is odd, and we're negating this statement, is this one. But an even more accurate way to put it would have been to say then one number is odd or one number is even. So it's just different ways to look at it. As you see, there's multiple different ways to look at this. Technically, they are all correct. So technically speaking, they are correct, but it's vague saying they're correct. All right. Sorry about the noise in the background. Ringtone for someone. So we looked at negation, we looked at inverse, and we looked at contrapositive. So let's go ahead and have a look at the very last thing we're going to be looking at for this chapter, and it's called biconditional. The biconditional combines this combination of conditional, the P implies Q, and its converse, Q implies P. The resulting compound statement is P implies Q, and it's read as P is if and only if Q. So if you ever heard, I will do this if and only if you do this. I believe I've even said this a few times during class. So when P and Q have the same truth value, biconditional is true. When they have opposite truth values, it's false. So we're kind of looking here. We're hoping that if we get a true statement going forward and a true statement going backwards, then we have a true biconditional. But if we have a false statement going forwards and a false statement going backwards, then we still have a true biconditional. But if anything else, we results in not an if only if statement. So let's go ahead and have a toy around with this. Not sure why that happens. Let's just go and clear that up. So let's just move this down right now. So if n is an even number that is not 2, then n is not prime. So the if is n is an even number. The n then is not an even number that is not 2. So we're switching it. So n is an even number that is not 2, then it's not n is not a prime. So we're saying if n is not a prime, then n is an even number that is not 2. Is this a biconditional? So we see that the if and then is false. The false converse is not biconditional. Because if n is not prime, then n is an even number that's not 2. Well, 9 is not prime, and 9 is a counterexample, because then 9 is not even. That's not 2. So we can just use little ones like that. 21 is another one. So if two lines never intersect, they are parallel, is the statement. And it's a good thing we're talking about this, because we'll be talking about parallel lines starting here pretty soon. That's the next chapter. So if two lines never intersect, then they are parallel. The original statement is true. So if two lines are parallel, then they never intersect. Is that true? Yeah, I would say yeah. So that's true as well. So we can conclude that yes, this is a biconditional. All right, so we have some classwork today, and if you finish up early, there was a chance that you might have a handout as well if you start to mess around too much. So might not want to keep on your best behaviors if I'm out there. Have a nice one, and just remember we do have a test soon. Bye-bye.